Hello, Calc 2 students. This is the first part of the lecture on section 9.1 to make up for the bad visual quality, shall we say, of the Cisco WebEx today's class. Today is March 29th, 2022. So I'm making these recordings so that you have a set of recorded lecture notes to work with. Okay, so we tried talking about how a sequence is like a function. You can kind of think of it as a subset of a function. So functions generally have been going from a real valued function of a real variable, and you could think of it as one real line getting mapped to another real line, or what we usually do is we take this second real line and rotate it 90 degrees and graph pairs of points, x, f of x, right? That's how we display our functions. Well, in a similar manner, we could display what a sequence is. This curve, for example, here is f of x equal to 1 over x. So this would be, every point on here is x comma 1 over x. And now if instead of allowing x to be any real number in the domain of the function, so back over here we would have a big hole at 0, because that's not in the domain of f of x equal to 1 over x. But if we took, instead of mapping the whole real line, a whole non-zero real line over to the reals, if we just examined it at the positive integers and looked at their images. So a way of thinking of it is take the graph of the real valued function and just grab those points above the natural numbers. 1, 2, 3, 4, and so on. We use different notation for a sequence than for a function. Instead of calling this f of n, we call this a sub n. But we do make this kind of assertion during this section. If these two functions are related as they are here, if a sub n is equal to 1 over n, then you can think of all these a sub n values, 1, 1/2, 1/3, 1/4, as just a subset of all the f of x values, which would be represented by all the y values, all the second coordinates of all these points up here. So we just examine a kind of skeleton of this function, 1 over x, just the part that's been coming from changing the domain from r star to the natural numbers, starting with 1. Okay, so sequences are really functions. All right. We have a theorem 9.1 in this section. If you know that the limit of f of x, the real valued function of a real variable, is equal to L, a finite real number. And if you take a sub n, a subset of all the f of x values, in other words, a sub n is the same thing as f of n, the function f, just only when we regard it as a function of a natural number, then we can assert that the limit of the sequence is equal to L. Now remember, this was defined, this phrase, the limit of a sub n equaling L as n approaches infinity, this has a very specific definition, right? Its definition is that for all epsilon greater than 0, there exists some m such that for all n greater than m, f of n minus L should be less than epsilon. Now, of course, instead of writing f of n in the definition of the limit of a sequence, we write a sub n right there. So that's what we would need to prove to show this theorem is true. So let some epsilon be chosen. Remind yourself about the definition of the limit of a function as x approaches infinity being a finite quantity. That's from section 3.5. That definition looks like this. For L epsilon greater than 0, there exists some, again, big number m, such that for all x greater than m, for all the x's, for all real values greater than m, f of x minus L, in the distance between them must be less than epsilon. So therefore, since it has to be true for all x greater than n, it certainly has to be true for all natural numbers greater than n. If you just replace the x here with an n, this will also follow. And remember that f of n is just another way of saying a sub n. So we have that theorem proved. We have properties of sequences in theorem 9.2, very much like the theorem, this is all like theorem 1.2 in section 1.2 about functions, that if you have the limit of a sequence is equal to some finite real number, and the limit of b sub n is some other finite number, or b sub n is another sequence, then theorem 9.2 says the limit of the sum or difference of those two sequences is going to be equal to the sum or difference of their limits. The limit of a constant, c, times a sequence, the c can be brought out front. Again, just by probably using theorem 9.1 here and the theorem back in theorem 1.2 back in section 1.2. Same thing, okay, with the product of two sequence elements. But let me reiterate that this does not apply when either L1 or L2 is plus or minus infinity. Okay, this example turned out not to work. I'm just looking at this again. That was not a good example, but this example is pretty good. For example, the limit of a sub n equaling 1 over n, that goes to 0, right? Its limit is 0. The limit of just b sub n, which is just equal to n, that goes to infinity. Now 1, the limit of 1, of course, is constant function, constant sequence. That's just going to stay at 1. It doesn't care what n is doing. But 1 can be rewritten as 1 over n times n. So if you think that this applies when one of these is infinite, you might make the mistake of assuming the limit of this product is equal to the product of the limits. And so then you would go around saying that 0 times infinity is equal to 1. That's a contradiction, okay? So this theorem only that you can look at the limit of a product of sequences and take the product of their limits only applies if these two L1 and L2 are finite quantities. Let's see now. Theorem 9.3. Again, we're borrowing from theorem 1.8, the squeeze theorem in section 1.3. It was written here in blue, and I'm just rewriting over it in green, referring to sequences instead. So everything that's written here about sequences we can get by converting to the related functions, proving that the property of the squeeze theorem is true in chapter 1, and then converting back into sequences. So if we have 3 sequences that satisfy an inequality like this, And the limit of this one, the lower one, is L1. The limit of the upper one is L2 as n goes to infinity. Then the limit of the one in the middle. Oh, sorry, excuse me. If we have 1, 2, and I should say 3, so we have 3 conditions here. If this inequality holds, if these 2 limits exist, and of course, these 2 limits are equal to the one number L. So if both of these are equal to L, then what's going to happen is that the one trapped in the middle, the limit of it, C sub n, as n approaches infinity, is also going to be equal to L. Okay? So we're borrowing a lot from what you learned about limits in chapter 1. Here's another one, another theorem about sequences. This one isn't, strictly speaking, something we borrowed from chapter 1. Here we're just using the definition of a limit, the epsilon m definition of a limit of a sequence, to get there ourselves. So for a sequent a sub n, if you know that the absolute value of the a sub n's in the limit as n goes to infinity is equal to 0, if you have that, then you can assume the limit of the sequence without the absolute values is also equal to 0. Very handy. Often you can, using absolute values, wedge something, show its distance from 0, show it is approaching 0 in absolute values, and this just allows you to just take off those absolute values. Why is that? To show that this limit exists, by the epsilon m definition of the limit of a sequence, we would have to show that for all epsilon there exists some large m such that for all, that's a notation that means for all n greater than that m, it's going to imply that the distance between a sub n and 0 is less than epsilon. Okay, that's our goal. We already have this, that there exists some large number, let's call it m1, such that for all n greater than n1, we get in absolute value, the distance between the absolute value of a sub n minus 0 is less than epsilon. Well, subtracting 0 doesn't make any difference, so we're looking at the absolute value of the absolute value of a sub n. A sub n is some real number. Of course, that's the same thing as just the absolute value of a sub n, and that's all we needed. This implies we've got our assertion. For any epsilon greater than 0, there was some m value such that for all n greater than that, we got our a sub n's arbitrarily close to 0. I could put a minus 0 in here if you like, and then it looks exactly like the definition of the limit of a sub n being equal to 0. So I would call that the first part of section 9.1.